Thanks. Okay, so what I'm going to talk about are two different things that relate to relativistic flows. And in particular, I'm going to discuss high-resolution adaptive mesh refinement hydrodynamical models of GRB afterglow jets. So these are extremely difficult calculations, but I'm going to show you, hopefully convince you that we've resolved the GRB afterglow jet in 2 dimensions. So it's an axisymmetric simulation using 16 levels of adaptive mesh refinement, and I'll discuss that in a second. And from that outflow, we've calculated the synchrotron light curves for what you'd see if you were on axis or at a range of off-axis angles. And we've also done it at a constant density and a wind medium, and I'll discuss that. The second topic is how to generate magnetic fields in GRB afterglow jets, and the idea here is that there's some Kelvin-Helmholtz instability that winds up a weak seed field, and we find that the saturation field strength is 0.5%. So epsilon B from relativistic MHD turbulence saturates at 5 × 10⁻⁻3. Okay, so whoops, the story everyone knows is that we're talking about an afterglow jet, so we're not talking about the engine, we're talking about some jet made by the progenitor that travels far away from the engine and drives a shock into the ISM, and that shock is thought to be a patch of a Blandford-McKee solution if it sets up, let's say, a theta of 0.1 or 0.2 in angular size. So we don't see the engine directly, and the engine is supposed to come from either merger of binaries or a Clap star, which we've heard discussed. So the point is that this jet kind of gets out of the star, and it drives a strong shock through the star, and it's confined by the ram pressure of a cocoon that it generates. And this is an AMR simulation in 2D showing the formation of a cocoon around a relativistic core of a jet. And the idea is that this thing breaks out of the surface of the star and drives a shock into that ISM. Okay, and that jet could either be a baryonic or leptonic, or it could be a magnetized jet, as we've heard earlier. But in both cases, it'll drive a shock into the surrounding medium. It's worth mentioning, I just wanted to note that the engines themselves can last for a long time. So this is kind of an old simulation that we did of the Clap star, but the Clap star drove a weak explosion in the equatorial regions of the star, and there was fallback for days. So people have been talking about engines that die slowly. We found that the engine can last for hours to days. Okay, but to keep things very simple, the basic idea for a fireball is that you deposit a lot of energy into a small region quickly, and that's going to expand due to its overpressure, and if there's enough energy here, the shock that it drives will be relativistic. And that's actually a very challenging thing to do. So if we have an energy to mass ratio of 100, we find that that drives a very thin structure, and the problem numerically, is that you can even see it, is that energy is swept up into a very thin shell of thickness 1/gamma². So it's extremely hard to resolve this. In 1D it's easy, but in 2D it's very hard. You have basically a hair that's traveling through the lab frame. And we can show here that we do get up to gammas of about 100 in 1D. And then also that in order to resolve it, what we need to do is use something called adaptive mesh refinement. So these blue lines show blocks of 8 zones. And what this technique does is it puts the resolution where you need it and removes it where you don't need it. So this is just, of course, in 1D, but in multi-D this saves you a lot. So it allows us to solve a simulation which is effectively at an incredibly high resolution without using high resolution where it's not needed. And doing these types of simulations, we can go from the Blandford-McKee solution to the Sudhoff solution at late times. But the difficult part is this non-relativistic transition. So we know what it should be like at early times and late times, but we don't know how so we need to solve this part numerically. We also need to look about jet spreading. So initially the jet is beamed just relativistically, but as it slows down, of course, it's going to start to spread sideways. So that has to be solved numerically as well. And then at late times, it's going to go into the Sudhoff phase, so the explosion becomes Newtonian. Okay, so I'm going to just point out something that's kind of technical, but it's really important to emphasize because it's a numerical problem. What we're talking about is a relativistic shock, and we want to know what the flow is laterally behind that shock. So we have relativistically hot, relativistically fast gas in this direction that's trying to move sideways. As it turns out, that's not easy to solve numerically in multi-D. And the reason is because this is just Newtonian hydrodynamics and relativistic hydrodynamics. And the point is that we have these powers of the Lorentz factor, and the Lorentz factor obviously depends on the velocity in all directions. So if you have a velocity in this direction, it's going to affect your dynamics in the lateral direction. As it turns out, that poses a numerical challenge. And I'll just show you quickly, we test for these things by setting up shock tubes, which are regions where we have a fast flow on one side or a high pressure flow that's driving a shock to the right. And this is very well understood and analytic solutions are known. But the challenge is when there's a transverse velocity component, even at high resolution, the solutions are wrong. So the black lines are exact solutions, and the blue lines here are the numerical solution at extremely high resolution. These tests are usually shown with 100 zones. This is with 400 zones. And that under-resolved simulations are just wrong. They get the wrong position of the shock. So the dynamics is not captured correctly. And in order to solve that, you need to use extremely high resolution. And the problem is actually this little wiggle here, which is the contact discontinuity between the shock gas and the unshocked gas. So that causes a problem, and it gets the dynamics wrong. So we've been able to solve this just by using adaptive mesh refinement, increasing resolution to resolve the structure so that we get the correct, there's still some inaccuracies, but we get the correct position of the shock. So we can go to very high effective resolution in the regions where it's needed. Okay, and the other thing has already been brought up, is that we're talking about a relativistic explosion, but it's going into a cold medium, which is not relativistically hot. So the equation of state that we need to use, so if you look, this is effective gamma, so that's the ratio of specific heats. And on the right, it's 5/3, but in the shock, there's a transition. The gas is kind of semi-relativistic, and post-shock, it's completely relativistic. So we can allow for the accurate equation of state by using this kind of interpolation where theta is like the temperature. So the cold upstream gas has 5/3, the shock gas has 4/3, and this is very important in GeoPree outflows because the shocks behind the main shock are not necessarily relativistic. So the gas, and also as the explosion becomes non-relativistic, it becomes a 5/3 gas. So it's very important to include the proper equation of state. And we can show that if you use a 4/3 everywhere, you get a very different and incorrect solution. Okay, another aspect of this code is that it's fifth order accurate in space, and that's very important because we really need high resolution to resolve the dynamics behind this very thin shock. And we've shown and published that this method, so-called WINO, is fifth order accurate in space and time. So that's a significant improvement over old methods. So what do? We set up a Blanford-McKee initial condition. So we've got a Lorentz factor of the shock at 23. And we've resolved it well. So we have thousands of zones across so this is an angular patch out to angle of 0.2. And we have 17 zones radial zones in this very thin shell. And we use what amounts to the equivalent of 40 billion zones. And we solve, it's a 10 to the 53 erg EISO. And in a density for this fiducial model of 1 proton per cc. And we start with a theta jet of 0.2. So the Lorentz factor is larger than 1 over theta jet. And then this is what happens. This is a movie where the movie is kind of zooming in. So you can see, as you expect, you drive what's initially a jet-like explosion, but after it slows down, it starts to expand. And we run this for a very long time. Ignore that. It goes to 150 years. So eventually it becomes like a supernova remnant, where you have a non-relativistic quasi-spherical shock. Okay, so the different phases are, you start out with a patch, that's a jet, the Blanford-McKee, and then there's several things that happen. The rarefaction travels inwards towards the axis, but it's slightly complicated. There's also a reverse shock here, and what eventually happens is as this material moves sideways, it slows down a bit because it starts to sweep up more mass. But the dynamics isn't as simple as a top hat that just gets lower in Lorentz factor and wider in angle. It's not like that at all. And then at late times, actually it stays aspherical for a long time. This is when the plasmas are usually considered to be non-relativistic and spherical, and we find that they're still relativistic and jetted. So it takes much longer to slow down and isotropize a relativistic flow than has been previously estimated. And we can compare our solution to the exact solutions. So here we have the Blanford-McKee solution, which we match initially, and then these are at different angles. This is on axis, and this is at pi over 4. And then eventually we converge onto the set-off solution, especially for the energy density in the gas. It starts off Blanford-McKee and becomes set off at late times. Okay, so the energy spreading is not simple. What happens is you start with a top hat, but then there's this rarefaction that travels in. It's not like you just get a top hat that's wider. And so this dynamics is what we've solved for. And at very late times, we start to get a spherical explosion. But this is different than analytic models for the afterglow evolution. So, and what we find is that the analytic estimates show very rapid spreading and becoming spherical. For us, it's much slower. This is where 99% of the energy is. It takes much longer for the energy to spread to large angles. Okay, but from all this information that we have, we can calculate exactly what the synchrotron light curve is that you detect. We know what all the fluid is doing everywhere at all times, so we can just add up the synchrotron emission using the standard models and calculate the light curve as a function of time. So these light curves are calculated from fully resolved 2D simulations of a relativistic jet from the radio through the X-ray. So we have multi-band light curves, and we can show how they match different analytic estimates. We do calculate pretty sharp jet breaks, although they're not very sharp, they're kind of curved, so this alpha changes as a function of time. And also we find at late times that we transition to this Newtonian case. So there's a flattening of the light curve, and there's also, this dot here is the counterjet. So at late times, the material that's moving away from you has slowed down enough that you start to see it. It's no longer beamed away from you. Okay, so these we've just published, it was just accepted, and we're doing other models currently, including off-axis. So this is difficult. Every zone becomes a torus, and we have to create 3D data, but we've done it. And you can see that, in fact, the jet breaks are much shallower. So there's much less of a jet break if you're just even slightly off-axis. This is just 0.1 radians off-axis. And then you don't see the burst at first. You only see the afterglow picking up later. So these are our predictions for what off-axis afterglows should look like. The second thing we're doing now, this is in preparation, is that in a wind medium. So there's a different dynamic, so we can calculate light curves for that as well. I'll have to quickly just say that we're motivated to study the amplification of magnetic fields, because this is a very simple model that you have a spherical shock in a constant density or smooth medium. In reality, we expect Wolf-Rayet winds to be clumpy. So as the shock crosses these clumps, it generates vorticity. And the idea is that that vorticity winds up any seed magnetic field and amplifies it. It's a very simple process. And the idea is that we know the growth rate of shocks that are hitting clumps. And what happens is the shock kind of wraps around the clump and it heals itself. They're very robust, but they generate vorticity in the post-shock flow. And if there's a magnetic field line there, it'll be twisted up. And so this just shows the velocity field of a spherical cloud that's hitting the shock, and it's generating vorticity here. And the idea is that these roll-ups are what twist magnetic field. So that the real blast wave looks something like this. It's hitting lots of clumps, so seed magnetic field is twisted. So, and the other thing we know is that jet outflows are probably shear-like. So they're faster in the center, like we saw from the jet coming out of a star. We expect slower material on the sides. So, and even more complicated, we probably have a shear-like jet hitting clumps. So there's many sources of vorticity. Also, for internal shocks, we don't expect them to be so perfect. They're probably misaligned or oblique or weird-looking. And so this motivates us to consider the Kelvin-Helmholtz instability in relativistically hot gas. And the idea is that we're just looking at a little patch of shear from either these cloud collisions or from the shear. So we're looking at a 3D periodic box with a P over rho, so relativistically hot, and a Lorentz factor of the shear of half the speed of light. So those are the conditions we expect from both these cases. And this is unstable to the Kelvin-Helmholtz mode, which is well known. And the main thing is that this also goes to turbulence. Once you generate Kelvin-Helmholtz, you grow it on smaller and smaller scales, so the flow becomes fully turbulent. And we've looked at this was in 2D, but recently we've done three-dimensional simulations, and the idea is we want to look at how very weak initial field lines are just twisted, so the magnetic flux doesn't go up, but the magnetic energy can be greatly increased. And so this is showing a shearing box in 3D. It's 1024 cubes, this is very high resolution, and this flow is coming towards you, that's going away from you. And we've perturbed this interface, and what you'll see here is the magnetic energy density. So already from the growth of the instability, you're starting to see stronger magnetic field at the interface. We're just rotating so you can see different directions. As time goes on, the instability is going to grow into the nonlinear phase, and all of the energy from the shear is going to go into turbulence. But that turbulence is going to continually twist the magnetic field. So you can see it's growing like crazy. It's already grown by 4 orders of magnitude. Then we're going to rotate again. And now you can see it's becoming almost completely turbulent. It's going to become that in a second. And what we'll see is that the net magnetic field, if you add up the total magnetic field and the total energy in the box at late times, that it's 0.5%. So that's where it saturates. Local patches that are red are saturated. So the magnetic field can't grow anymore because if you try to twist the fields there, they'll snap back because the field is too strong locally. But if you have a turbulent spectrum, which we've calculated, from that we can calculate how much energy should be in a magnetic field. And so what we find at late times is that this value converges to 10 to the minus 3. Okay, so
10 to the minus 3 of the
5 times 10 to the minus 3 of the total energy.
Partition.
Yes. Okay, and then what we've also done here is we've calculated that, I think I'm done here. Yeah, okay. So, and we've calculated the power spectrum for the first time of relativistic MHD turbulence. We find that it's close to 5/3, but this is the mildly relativistic case, and we're doing other cases as well. Okay, I'll just leave the conclusions up. Thanks.
Does that mean that you would expect maybe an ordered field in a thin layer, and then behind it basically a very turbulent field?
No, just a weak turbulent field from whatever's there from initially, and then after the shock passes, it's twisted.
Yeah, what do you actually see in the shock though? I mean, in the shock you're going to get an ordered field, aren't you?
Although you're going to compress whatever field was there to begin with, but that'd still be weak. That would still be weak given the strengths of typical fields in the ISM. So by the time there's any realistic field, it'll be very tangled.
From the point of view of polarization observations.
Right.
You can actually do polarization observations. Basically, you see a thin structure with a significant degree of polarization, but then behind it, it would
be less polarized. That's exactly right. Yeah. Oh, you're still got. Go ahead.
You were saying mildly relativistic turbulence. Do you mean that the turbulent motions are mildly relativistic, or the initial shock is mildly relativistic?
The initial shock is relativistic, or it might have Lorentz vector of a few. But the key thing is that the temperature, the plasma, is relativistically hot. The thermal motions of the particles are relativistic.
Okay, the bulk motion of the relativistic
is not. In fact, I think if it were, it would be supersonic and it would shock immediately, and the energy would go into internal relativistic motion instead of turbulence. So there are these models that want to have gamma 10 eddies, and I don't think those will work. I'm actually checking that right now.
I fully agree.
Okay, thank you.
That's what I
okay, yeah.
Yeah, so Andrei Buzilov on the...
Sorry?
Andrei Buzilov in his paper showing that in the bottom McKee phase, the blast flow is non-universal in the sense that if you do a perturbation, it decays, but very, very slowly. So I was wondering if you confirm this.
Yeah, that's exactly that's one of the projects that we're doing right now, is it's not even clear that you set up Blandford-McKee from a jet that interacts. Is that what you mean, right? Yeah. So he thinks there's a different attractor which gives a different function of energy, and Lorentz vector is a function of angle. Yes, we are checking that right now. But for this simulation, we want to make contact with what's been done previously, so we did just standard Blandford-McKee. But we are checking that. So we're putting a jet into an ISM and seeing what kind of shock it sets up. And we're going to check whether Andrei's solution is right. Yeah?
Calculating the spectrum, you just simply assume that there's some Green's constant. You didn't take this. When you show that you calculate the spectrum,
right,
your first simulation,
right,
there you just assume constant magnetic field. You did not take it.
Right, that was standard. Yeah, so we used a constant epsilon b, constant epsilon e. We did everything as close as possible to what's generally done, and all we did is change the analytic flow to a computed one. Yeah.
About the spectrum of turbulence, you have periodic conditions, yes, in this case. Is there any influence coming from this periodic condition, from the point of view that if your disturbance travels this way, it continues to travel, so it grows infinitely long. And I can imagine that possibly in the longest wavelengths you can artificially grow something that cannot be in a real situation.
So effectively, we don't have those wavelengths. So we're cut off by the largest wavelength we can fit in our box, and we don't believe anything larger than that.
Okay.
So just kind of, yeah, it's kind of like a cutoff. Yeah. Okay, yeah.
Have you done these simulations with different Lorentz factors, and how does the epsilon b depend on that?
Right, so that's what we're doing. We've done a grid of 3 Lorentz factors and 3 temperatures, and we're analyzing those right now. So this is the first one we did, and so that's to be. Stay tuned. Yeah, we'll see how it depends. Yeah. Yeah.
In order to have a saturation, we need to have some numerical resistivity or something like that. And,
Right.
The saturation level depends on that.
Absolutely. So this is a we have a numerical resistivity. So we don't. It's not. So that's a test of the quality of our code. So all we can do is increase resolution and see if we've converged, which is what we did for this epsilon b of 0.5%.
So it converged.
It converged, yeah. So we did it at a bunch of different resolutions in order to check. So sorry, I should have said this is 512 cubed, 768 cubed, 1024 cubed. If we start at a higher value, we're seeing convergence. That's our claim right here that we've converged up there.
Okay, I think we leave any further questions to Andrew till later on if you have them. So let's thank him again. Okay, so our next speaker of today is Miguel Angel Aloy, who will tell us about the simulations of relativistic jets in GRB progenitors.
Thank you. So I'm afraid this is not going to be an observer's view, but rather a theoretical view of progenitors, of simulations of relativistic jet progenitors of long gamma ray bursts. I have been done this work in collaboration with a number of people, many of them at the Max Planck Institute for Astrophysics and some in Valencia. So now I would say that our current understanding of gamma ray burst outflows is that GRBs are like the birth cries of stellar mass black holes. Whenever you have the birth of such an object, then you may have one of those events. In other systems where we have accreting or hyperaccreting black holes that fuel relativistic jets, for example AGNs or black hole X-ray binaries, there is a direct evidence that there are relativistic outflows and that those are collimated because we see the jets. So in principle it's reasonable to believe that also gamma ray bursts are the result of relativistic and collimated outflows in this kind of stellar mass black holes, accreting stellar mass black holes. But note that I stress these two points, and this is because theoretically, well, at the observational level, we know that this outflow should be relativistic, mostly because we see this radio scintillation of the interstellar medium, superluminal proper motions in IMH afterglows, and from the theoretical point of view, we have to overcome the compactness problem. But the evidence for collimation is only indirect, I would say, because the observational constraints, have been challenged by the observations of Swift. So it's not so clear, although we have heard some talks during these days, that there are those achromatic breaks or chromatic breaks in light curves that there used to be some time ago. On the other hand, theoretical constraints are used to say that if you have collimated outflow, of course you reduce the energy budget, which is also desirable. But to me, what is important is that most of the simulations, or I would say all the simulations doing progenitors of GRBs, of GRB jets, show that if you have an outflow, this outflow is collimated. So here I put just some examples of people who have been working on that. If someone in the audience is not here and should be there, just let me know, but it's just some examples. Now, I don't have to tell much about the model of choice for progenitors of long gamma ray bursts, because there have been some talks already, simply to say that the collapsar model is the model of choice in this case. Well, I don't enter into details here, but what simulations have shown is that there are several points that have been established. For example, the collimation of the jets. If the jets are started by means of deposition of thermal energy, as it could be the case if they are initiated by the deposition of energy by neutrinos, then these jets are collimated by the progenitor star. There is inertial confinement. Otherwise, if you have a magnetic field, you may have self-confinement of the jet, right, by this by toroidal magnetic fields. But what you're looking here is a movie of the resonance density of some model that I ran time ago of a jet making its way through a Wolf-Rayet star, a collapsar model, say, and eventually leaving the star surface and producing a seed for a gamma ray burst later on. Now, the open angle when the jet breaks the surface of the star has been determined to be in many simulations of a few degrees, right? Even can be quite wide angle according to some simulations, depending on the conditions that you set. Or recently, during this week, Sergei Komisarov has told us that if you have a magnetic initiation, maybe those jets might be collimated in extremely narrow pencils. On the other hand, these jets show a lot of transverse structure, not only along the radial direction, but also across the jet, right? The typical picture that emerges in these simulations is that you have a fast spine where the outflow is ultra-relativistic with Lorentz factors about a few tens or hundreds, depending on the time of evolution of these jets. And then this core is surrounded by a sheath where the flow is much slower and basically catches up with zero velocity in the external medium. Now, the variability in the outflow, it's imprinted by several waves. On the one hand, once the jet starts to propagate through the star, it's unavoidable that it will be prone to Kelvin-Helmholtz, shear-driven, or pinch-emitted instabilities. I like to call this variability extrinsic variability. Those are profiles of the Lorentz factor along the jet axis, and you see how variable it can be as the jet moves along the star. This variability can be source of internal shocks. Here, the jet is still opaque, so radiation cannot escape. So if you thermalize part of the kinetic energy, that's not a problem because that can be reused for later acceleration. Now, one of the problems is that the intrinsic source variability is indistinguishable, in my opinion, from that produced by the propagation of the jet inside of the star. Well, you know, it's going to be hard by looking at light curves what is the true variability of the inner engine and what is just the variability because of the evolution of the jet. According to the claims of Morsoni and co-workers, maybe if the jet is long enough in the latest tail of the jet, so in the tail of the gamma ray burst emission, one may see if the inner engine is variable, one may see some variability over there, but that's to be tested. Jets have been shown to be stable in three-dimensional relativistic hydrodynamic simulations, but it's still to be proven that they are stable to kink instabilities in three-dimensional relativistic magnetohydrodynamic models. Now, in the recent work that I have been doing with Akira Mitsuta, we have explored a parameter range which was not explored so far, which was the dependence of the outflow properties with the kind of progenitor model that we have, basically with the mass and the metallicity of the progenitor. So we took a bunch of models from Heger's webpage, which are pre-supernova models, right? Basically bare helium cores, which are meant to be what you have after you lose the hydrogen envelope of those massive stars. And then we have injected into all these models jets with the same characteristics, meaning that we put injection conditions at about 1,000 kilometers from the center of the star, and we fix Lorentz factor 5. The jets are relatively hot with the internal energy per unit of mass of the order of 30 times the speed of light squared. They are open, they have an initial open angle of 5 degrees. We inject for a relatively short period of time, after which the power decays linearly, and we put there about 10 to the 51 Hz per second as luminosity of the jet, which means that we release a few 10 to the 51 Hz in total. Right, so models can be clustered in three classes. Models with relatively high mass, with masses around 15 solar masses, intermediate mass, about 10 solar masses, and low mass, about 5 solar masses. This is because in those models, Heger has put some laws due to winds, right, of different strengths, parameterizing the uncertainties that we may have in the latest phases of stellar evolution.
So those are the masses after mass loss.
Yes, yes. At the end, just before, well, what they call the pre-supernova model, when you link with potential explosions. Oh, sorry. We also explored metallicity, so solar metallicity models and solar metal poor models. But we will see, as I will show you, there is no big difference in this regard. So the progenitors fill up our domain, which extends up to 10 to the 11 centimeters, but are endowed when they finish by some atmosphere, which can be either a constant ISM with a density of the order of 10 to minus 6 grams per cc, or a uniform or a wind profile, right? Here you have some prototype examples of different classes of models, low, intermediate, and high mass. This is the density along the, well, this is also a spherical symmetric model, so this is the density profile with versus radius, and this is for metal poor models. Now, it's important that what we were more concerned about was about the distribution of the energy per unit of solid angle when the jet breaks up the surface of the star and evolves eventually, right? These jets turn out to become almost self-similar after a few 10 to the 10 centimeters. So more or less this is what you may expect in the long term for the distribution of energy versus angle. And what we find is that this distribution, this energy per unit of solid angle can be quite well fitted by a smoothly broken power loss, right, with a power law index close to 0 in the intrinsic energy distribution, not in the isotropic equivalent, as I will show you. And then they decay quite steeply over here, up to about 3 or 4 degrees. Here these hums are produced by the cocoon contribution in those jets, which is much hotter and just sticks out of these fits. Now, well, I don't have much time to go into these details, but the only difference with metallicity comes in the cocoon contribution, which seems to be a bit steeper for low metallicity models, but I don't have the time to enter into the details. What is important is that there is a proportionality between the progenitor mass and the post-break index in this smoothly broken power law. So if you plot this index versus the progenitor mass, you see that there is a wide scatter but rough proportionality of this index with the mass. Likewise with the mass loss rate, because in the end the final mass of the progenitor is determined by this mass loss rate. And the large dispersion is produced simply because we have a bunch of different density profiles for the same final mass. For example, these are all similar masses, but this is log scale, so there might be a factor of 2 or 3 in some points difference, or even factor of 10 over here in some cases. Right? That's what is causing the scattering in the models. Now, when you look at the equivalent isotropic energy per unit of solid angle, so what you probably may observe, you have that the distribution changes a bit, that you don't have this flat course, instead you have a core that goes like a power to -1, so this is the pre-break power law index, and the post-break power law index is also a bit steeper. So we have only a little bit of consistency with the analytic model of Lazzati and Begelman, which claims that the isotropic equivalent energy is proportional to theta to the -2. This is only probably true in the cocoon, but not in the jet core or in the jet shear layer. Now, why is there a correlation in this index and MP? We have pinpointed this to the fact that smaller mass progenitors have a smaller average density. And then the jets can propagate faster there. And this makes that, this fast propagation, in the end, what makes is that you cannot inflate so much the cocoon. Most of the energy is put to push forward the Mach disk. And that's what makes these jets in low mass progenitors narrower. Now we have also estimated which is the probability that you see the detectability with the Bwin angle for this kind of jets, and we see that again, I mean, the fact that jets in high mass stars are poorly or worse collimated than in low mass progenitors makes that there is a higher probability of observing an event from a high mass progenitor than from a low mass progenitor. And I have plotted here also for comparison some of the curves, this solid thin curve, for much smaller, 1% of solar metallicity, and the influence of metallicity seems not to be crucial in this models. It's important to note that when you compare the detectability of collapsar jets and merger jets, they are quite different. Merger events are less collimated and have a flat core with very steep flanks. That is to say, the shear layer of these jets is much thinner, and therefore they display a non-negligible probability of being observed between up to say 10 or 13 degrees. While for collapsar jets, I mean, unless you look basically on axis, it's going to be difficult to detect them. Now, what else? I don't know if I have some 1 minute to go across this. It's about the dynamics of the outflow after we switch off the central engine. We, as I said, after 3 seconds of energy injection, we just switch off gradually the power in the jet. And then what happens is that the unshocked region of the jet, so the innermost part where the jet was expanding basically freely and it was like a relativistic wind, is lost because you refill this with matter from the side of the progenitor. You can see it clearly in the evolution of the rest mass density. This is density along the axis at different times. So when we switch off, this automatically refills and grows in density, which immediately translates into a decrease of the Lorentz factor in that unshocked region. Fortunately enough, these models are rather hot. So the shock part, in the shock part you have sufficient thermal energy to eventually speed up converting thermal into kinetic energy, and eventually we may go to Lorentz factors of a few hundred. And just the summary, the numerical modeling of progenitor systems involving newly born black holes has allowed us to gain a refined understanding of the dynamics of and the global properties of relativistic outflows generated in those systems. We find that the gross properties of such outflows are correlated with the mass of the progenitor, while the metallicity has a little impact. The simple analytic model of Latsatian-Legelmann is only marginally consistent with the distribution of energy in the cocoon, but not in the jet itself. But our models, on the other hand, coincide, are on the ballpark of what other numerical models predict. And collapsar jets are better collimated than merger jets, with a shallower decay of the equivalent isotropic energy per unit of solid angle. And finally, the better collimation of, that you find in low mass progenitors makes that you expect to see more events from high mass progenitors than from low mass ones. That's it. Thank you.
Various indications from observations suggest that jets are much larger, by a factor of 5.
Can you speak out louder, please?
Various indications from observations suggest that the jets are about 5 degrees or more. So at least 5 times wider.
Right.
So my question is, and if you fall up as steep like even theta to the minus 2.7, this means that there is not enough energy in the wings to see it from the outside. So either you see it or not.
Right.
And so how do you explain this discrepancy?
Okay, the only thing that, the thing that comes, and we explained that already some time ago, is that it depends on the radius of the progenitor. If the progenitor is very compact, then you don't have time to collimate much this jet, and then the jets can be wider. Indeed, as I said, some simulations show opening angles up to 20 degrees for collapsar jets, right? But the trend is that they are worse collimated, better collimated than in the case where you don't have such a inertially confining medium, for example, in merger events. But in this case, for this particular set of models that we have investigated, the result is that the opening angle is not too large, as I said, from 5 or 6 degrees, but the energy is rather concentrated towards the axis. And you're right, I mean, these models, if the progenitors are these ones, it's difficult to reconcile with some observational results, not with all, but with some. So this may mean that some of the, other progenitors should be tested. Indeed, the table of models of Heger is much longer than what we have here.
But in which direction can you go? I mean, you don't want to increase the masses below 5 solar masses.
Right, but this is because they have put, but the structure is determined also by the initial mass of the star. And Heger had models starting from, if I don't recall properly, 12, 16, and 30 solar masses. So we haven't tried neither the 12 nor the 30 solar masses models, which yield in general quite extended configurations, except some models with 12 solar masses which are rather reduced. So there's still some variability that we have not accounted for.
Okay. Can you try, can you try, I think the clearest value that is for 030329. So this is the case when the supernova is fairly well understood, the progenitor is fairly well understood, at least if you ask people to do supernova analysis. So you know how much mass was there,
right,
and you can guess what is the progenitor, right, and you have some idea what is the opening angle. So can you try this progenitor?
We wanted to try that, but the only problem is that the progenitor is very large. So it didn't fit properly in our computational domain with the resolution that we have. So this is our hope that we will get into that soon. So, but you're right. I mean, this is an idea that it's.
How large would have been the progenitor?
In these cases?
No, in that case.
I don't recall exactly, but it was a few times 10 to the 10, almost 10 to the 11, and our computational domain is 10 to the 11, so there's no time for the jet to leave and reach this self-similar phase in which we can make extrapolations. That wasn't involved.
We had the quick one over here.
How you expect what will change your results if you have a more spread star, like observed Wolf-Rayet stars? Usually weigh 10 times bigger than numerical models.
You mean because of winds, or because because they just are inflated?
No, weigh really bigger.
Right. Okay. If they are bigger,
if
the bigger, as I said, the larger is the radius of the star, the better collimation you get.
And a very quick one for myself.
Yeah, you mentioned in your result that a significant, say, fraction of the variability that is seen may not come from the intervention, but from lateral shock waves. Is there any way to quantitate, to give some quantitative result of that?
Hardly, because this is you are exciting Kelvin-Helmholtz modes as you move along the surface, along the progenitor. The problem here is that all this Kelvin-Helmholtz analysis in the linear phase or analytic developments are for pressure-matched jets, and where you have more or less uniform external medium. Whatever else you don't do in this way, you have to make approximations about how the Kelvin-Helmholtz mode saturate and how they depend on the radius. So it's very hard on analytical grounds and on numerical simulations to say this variability comes exactly from these Kelvin-Helmholtz modes. Everything is washed out because you have also angular spreading effects, and I don't think that we can say much about this, because consider that this variability will seed internal shocks. These internal shocks will collide much later, and they will yield the imprint in the front gamma ray burst phase. So it's a completely nonlinear process. I think it's difficult to.
Okay, let's thank the speaker again. Next up is Marco Nardini, who will tell us about a new view of gamma ray burst afterglows.
Good afternoon, I'm Marco Nardini. I'm a PhD student in SISSA, and I work in collaboration with Gabriele Ghizellini, Giancarlo Ghirlanda, and Annalisa Cilò. The launch of SWIFT satellite opened a new window in the early time observation of X-ray and optical JRB after. And what we found from these early time light curves is much more complex than what had been expected before the SWIFT launch. The first and most cited result is the peculiar early time X-ray light curve that we observe in a lot of JRBs. That is characterized, by, as you know, by a steep early time decay starting immediately after the end of the product emission, a shallow flat phase followed by the steeper decay phase that is almost what we observed before the sweet launch. Another interesting feature is the comparison between the optical and the X-ray emission. We sometimes have that the optical and the X-ray go together with almost parallel light curves. In other cases, we have quite simple power law behavior in the optical and the X-ray, but with different decay indices. But in a quite large number of cases, we simply have different optical and X-ray temporal evolution with the presence of chromatic breaks and different temporal indices. This complex scenario, triggered the interest of a lot of groups that tried to explain the nature of these findings. In particular, the nature of the flat phase observed in the X-rays and sometimes in optical triggered the interest of a lot of groups. Here I give you just a brief summary of the different models that have been proposed in last year, and I divided them into main groups. Some of the groups try to explain this flat phase with some modification of the standard afterglow emission. These are just part of the proposed models. Others are claiming some geometrical effects in order to explain this flat steep behavior. In this talk, I would like to focus my attention later on the so-called late prompt model proposed by Ghisellini in 2007, in which this flat phase and also the later steeper decay is produced by a late time activity of the central area. In order to analyze the optical and X-ray light curve in the host frame of the gamma ray burst, we selected a sample of long GRBs with no redshift, with a well-sampled optical and XRT light curves, and with non-host frame optical extinction. We found 33 GRBs fulfilling all these requests. We then tried to model the broadband optical and X-ray light curves as the sum of two separate components. The first component is simply the standard afterglow emission as analytically described, for example, by Panetesco and Kumar in 2000. The second component, at this first time, is treated in a completely phenomenological way. We try to explain the flat steep decay with this phenomenological component with different parameters. The parameters in which I'm really interested in this talk are the time of the break TA, the late time temporal decay index alpha steep, and the luminosity, the normalization, the luminosity at TA. Almost all the light curves are well fitted by the sum of these two components, where we are not considering the early time steep decay, the flaring activity, and the bump, sudden bumps that sometimes appear in the optical. We have different cases. Sometimes we have that the standard afterglow emission is able to explain both the optical and the afterglow, and the optical and X-ray emission. In other cases, we have that they are both well described by this second component. Let me call it component 2. Now, we have also mixed case in which, for example, usually the afterglow dominates in the optical bands, and component 2 dominates in the X-rays. And we sometimes have also some strong transition between one component to another. Now that we modeled the rest frame light course, we can try to go in the details of the component 2 parameters distribution in order to try to make a first step toward a more physical model that is able to describe this second component. An important thing is related to the late time temporal decay of the component 2 that cluster around this value 1.6 that is pretty close to this 5/3 that is related to the accretion rate of the folded material into the black hole, and it is very close to the value that describes the decreasing rate of the luminosity of the X-ray flares as found by Lazzati et al. When we take into account these parameters, that is the product of the time of the break and the luminosity at the time, that is roughly an estimate of the total energy emitted in the component 2, and we compare it with the E gamma ISO, that is the total energy emitted during the gamma ray prompt emission, we see that there is some sort of correlation that is much better than the one, for example, that we obtain comparing the gamma ISO with the energy emitted through the standard afterglow. There could be a first link between the standard gamma ray prompt emission and this component 2. As a possible scenario, we can try to see what this late prompt model that has been proposed by Iselin et al. 2007. In this model, the gamma ray emission, early prompt gamma ray emission, is described as done in the standard model. But the central engine keep going, producing shells with much smaller Lorentz factor for a much longer time. And when this gamma factor that is decreasing in time becomes equal to 1 over theta, where theta is the jet opening angle, we can see the break in the light curve between the shallow and the steep decay phase. At these late times, this optical and X-ray emission produced by this mechanism compete with the X-ray and optical emission produced by the standard afterglow emission. And we can see it as the representation of the two models, the two components modeling that we tried phenomenologically in the light curve modeling. Now I want to turn into the X-ray test of this model. When we have optical and X-ray light curve that are parallel, we can imagine that they are being produced by the same mechanism. And if we go to study the optical to X-ray SED, we can imagine, for example, that they lay in the same simple power SED connecting the optical and the X-ray. We can also imagine a broken power scenario for the SED, but in this case we have to require the break to be very steady in order to have this parallel optical and X-ray evolution. When instead we have different optical and X-ray temporal evolution, we can first of all test whether a moving break, for example a cooling break, can describe the observed behavior. If not, we can imagine that the optical and the X-ray, as I told you before, are produced by different mechanisms. In this case, we have to require the presence of a spectral break here, in order to avoid, for example, the X-ray mechanism to pollute the observed optical emission. This break could, in principle, sometimes fall inside the observed XRT bands. So we try to test in our in the GRBs in our sample whether a break can be found inside the XRT band. We select the sample of the GRBs with richest XRT spectra, and for 7 of them we found that a broken power law model gives a better fit. We are avoiding the flaring activity and early time speed decay. For 8 of them we can exclude this solution. Of course, this broken power law modeling has a strong implication, for example, on the NH column density, but for the lack of time I will not discuss it in this talk. If you have some question, I have a couple of data slides on this topic. We now want to test if the presence of this break in the X-rays is consistent with what we observe in optical. The first example is GRB 060729. We have that components 2 dominates both the bands. We take the SED and we see that it's consistent with one single component connecting the optical and the X-ray. This other burst, the optical is dominated by the afterglow and the X-ray by the component 2 here. We extract an SED and we see that the SED is inconsistent with being the same component. GRB 061126, we have that the X-ray is dominated by the component 2 for the wall light course, while in the early times the optical is dominated by the standard afterglow. We extracted NCD and it is inconsistent as discussed by Curly et al. For example, with a single component LCD. At later times, when component 2 dominates both, we have instead that the LCD is consistent with being the same mechanism, and we also have a transition and a changing in the optical spectral index. Now I would like to treat the last topic of my talk, and what are the jet? Like a question you already heard sometimes in this workshop. If no standard afterglow is observed, if the light curve is dominated by the component 2, we don't expect any jet. For example, in this case, 0610, 07, a burst you already have seen, is dominated in our scenario by the component 2 in the X-ray and by the afterglow in the optical. We don't see any evidence of jet break for a very long time in the X-rays. Here you find that the expected jet break times using the Ghirlanda relation, but unfortunately we don't have late time observation to test the presence of a break in the optical. When instead we have that the light curve is dominated by the standard afterglow, we expect a possible jet break. For example, here we have that the optical is dominated by the standard afterglow and we do see the break. In the X-ray is much more complex because here it's dominated by component 2. Now the standard afterglow becomes dominant. We can see the hint of the presence of a break, but there is some residual flux due to the component 2 that is making the break a little bit shallower than what we expect. The last case are achromatic break allowed. Yes, of course. In this case, the optical is dominated by the standard afterglow, we see the break. The X-rays, in our opinion, is dominated by the component 2. Here there is the TA, and after the TA we can see that we can put all the points in a single power law without any evidence of a break. In conclusion, if I have time, in conclusion, I've shown you that the optical and X-ray light curves are really complex in the Swift era. We try to model these light curves with two separate components, and we start to have some indication of a possible physical mechanism that can describe this component 2, and I can give a possible solution to the jet break issue. We then try to test this model also by a spectral point of view, with the search for breaks in the X-ray spectra, and with the comparison of what we observe in the optical. Thank you very much.
Any questions?
So how is the second component? The emission coming from central engine or some of these?
Sorry?
Yeah, just wonder the assumption about the second component.
So the assumption of the second component in the first light curve modeling are just to try to minimize the parameters of a purely phenomenological
Yes. How
model.
about your opinion? What kind of model you have now?
The one that we tried is this component by, say, a dynamical point of view, the one described by Giseli et al. That is this late prompt component with shells that are emitted by something that is related to the fallback material that can fall inside the black hole for quite a long time. And this one, the model that we try to test. I feel free to see any other model that can produce a similar light curve, that is simply a broken power law light curve that is able to stand for 10 to the
So material falling back to black hole and emitting directly from there?
I didn't enter the details also because the aim of our job, the first aim of our job was, let us try to disentangle the optical and the X-ray, try to minimize the parameters. Then we want, and this is future work, try to start from the parameter distribution of this phenomenological model to try to take some constraint on the physical model. The first good result is the 5/3 that is really, I think, the most interesting result by the of the first light curve modeling job. And then something that looks related, this second component, the energy emitted in the second component, with what is emitted during the prompt. And this is not true when you consider the standard afterglow emission. This correlation doesn't survive. So these are the first hints of a possible link with this physical model. And is in agreement, in principle, with what says a model like, for example, the late prompt model.
Well, this is not what you're trying to discuss, because you're not discussing the physical model, but I'm still wondering, when you talk about the fallback model, what is causing the rise? I can see why you have t to the minus 5 curve, but why would it just not work for the first 100 seconds or 200 seconds or more, and then start?
The rise that you say when we have first power going up?
Yes, the first
okay.
power going up.
The first power law is not tracing the fallback, but it's a geometrical effect. We have the gamma, the area that we are seeing that increasing because of the lowering of the gamma Lorentz factor of the incoming shells. And it's something that is similar to the jet brake, but seen by a completely different point of view. Then when the 1 over gamma is equal to the jet opening angle, we start to see really the decay that is this 5/3 that is related to the fallback. So the first power law is dominated by this combined effect of the decreasing Lorentz factor and the intrinsic fallback of 5/3 that we have in the background in the model.
But this means that you're not energy in this component. You're trying to argue that the energy in this component is comparable to the prompt energy. But if you're not seeing the whole emission because of the geometrical factor, you don't see the whole emission of the first of the second component, then you have a lot of energy. If you don't see the second component will be very, very
in this comparison, the energy emitted in this prompt is less than 1/10 of what has been seen in the standard prompt. And we are comparing the isotropic energy of the early prompt, say, emission, and an isotropic estimate of the energy emitted in the. So we have also taken into account this combined effect that we are not correcting for the jet angle the energy in the prompt also.
In general, the radiative efficiency during the prompt phase in this model will be extremely high.
It should be higher than the one that we predict in the standard shock. I didn't read it directly, but you can expect.
Okay, time for one last quick question.
So the parts of the two component has a large variation, or the standard afterglow has a large variation? Which controls the dominance?
Okay, in the different okay. Usually the second component is dominating in the X-rays in most of the cases, and the afterglow, standard afterglow, is dominating in the optical. We have also mixed condition and so on, but these are the numbers that were present in our paper. Usually the X-ray dominates is dominated by this second component, and the optical is standard afterglow. In the optical, remember that we sometimes also see the onset of the afterglow, and so we have that trade on it.
Okay, we'll have to leave it at that, so let's thank the speaker again. So finally this afternoon we have another one of our hosts, Felix Wright, and he's going to tell us about fuzzy black body, the fuzzy black body component in quantum emission on gamma ray bursts.
Okay, yeah. Thank you. So this work is mainly done together with Asaf Peer. He's giving a theoretical talk tomorrow, and these talks are heavily connected to each other, so I want you to see this as the first part of these two talks. So what I will do is I will motivate why one should expect to see a strong photosphere in the front face of gamma ray bursts. Then I'll show you what the observations look like. And then I will try to underline this interpretation by the recurring behavior we find of the photosphere. So a basic problem we have in gamma bursts is that we do not know the origin of the gamma rays during the first minutes of the observations we see. And it's during this period most of the radiation comes from. The basic picture of gamma bursts with the jet piercing through a Volta Ray star is well established, and we have a relativistic jet in which internal shocks or magnetic reconnection dissipates the energy and then which can then radiate. Given the general appearance of the spectrum as a broken power law with a peak, here's a low energy power law index and the high energy power law index beta, it is a reasonable assumption to say that the emission could be from optically thin synchrotron radiation from a power law distribution of electrons which are accelerated in the shocks. This means that the peak here is related to the minimum Lorentz factor of the electron distribution, and the high energy power law here reflects the distribution of the electrons, the power law distribution of electrons. The problems with this interpretation is mainly due to this low energy power law, which is significantly harder than what one expects from optically thin synchrotron radiation. Here's a distribution of a number of bursts with varying number of spectra with the low energy power law index here, and this gray line shows you what is expected from optically thin synchrotron radiation, alpha photon index minus 2/3. This means that these spectra that are to the right of this line are too hard to be explained by optically thin synchrotron radiation. Now, taking typical parameters of the relativistic outflow, comparing the cooling time with the typical dynamical time, you find that the electrons most probably are in the fast cooling regime, and this means that this expected power law is down at minus 1.5, and this means that most of the spectra that are seen are incompatible with this picture. The second thing comes from shock acceleration in relativistic shocks. What you typically find is not a straight power law, but you find that most of the energy resides in a relativistic Maxwellian. This is the distribution of electrons as a function of the Lorentz factor. Most of the energy resides in the relativistic Maxwellian, which is proportional to the bulk Lorentz factor. There is a power law, but this only has part of the energy. The third problem is which has been pointed out several times, the low efficiency of the internal shocks to extract energy. Now, there has been a lot of discussion of trying to solve this. I'll just mention a few. For example, jitter radiation and various versions of inverse Compton radiation has been invoked to explain how low energy power laws. The natural explanation, which I'm going to dwell on mostly here, is mainly here is the possibility of photospheric emission. Now, very early on in the early papers in the 1980s, based on the variability and the amount of energy available, there was a prediction that the gamma bursts should be thermal or have a strong thermal component. This was later quantified in more detail by Messrs. and Rees in 2000, where they argued that the gamma burst spectrum should consist of several different components: a thermal component and a non-thermal component from synchrotron shocks. Depending on the variability timescale at the central engine and the Lorentz factor, these components can be differently strong. In this particular case, there is a strong photosphere. In other cases, the photosphere is not visible. Similar discussions have been done on point flux models by Jager. Now, this is assuming non-dissipative acceleration, and all dissipation occurs in the optically thin region where we get the non-thermal components. Now, if you allow dissipation during the acceleration also below the photosphere, what can happen is that the kinetic energy of the outflow can be given back to the energy denser photons through compensation. This point was studied in more detail by Peer et al. In 2007, who showed how the feedback between the photons and electrons can, or the reprocessing of the electrons by the photospheric emission can produce various types of spectral shapes. Now this is pure theoretical arguments. Now recently Lassati presented a result where he did numerical simulations of a jet piercing through a Voltaire star, and this is what's happening below the photosphere. This colored code is the density. Now the important thing here, what he finds is that there are very strong oblique shocks occurring throughout the evolution of this jet. And this means that a lot of energy is dissipated throughout the jet, and the jet becomes very hot. And at the photosphere, there's a lot of thermal energy radiated. And what he finds is that this is the blue light curve is the total energy at the photosphere, and the red light curve, the red curve here is the amount of thermal energy that is residing at the photosphere. And this sort of radiative efficiency, these two divided by each other, can rise to very high. This is 0.8 here. Now, so these are motivations of you could expect very strong photospheric emission, and of course then one goes into the spectra to see if we can see anything. Before I show you the spectra, I'll just point out the basic point, which is obvious but nonetheless very important. That is spectral evolution during the prompt phase. This is a light curve, and these diamonds are the peak energy that we find. And you see that they are strongly correlated. And this is also seen here in this plot, where this is the instantaneous luminosity versus the instantaneous peak energy. And there's a very strong polar correlation, which is the Gordianetsky relation, which was discovered in 1983 already. So this means that the spectra are moving around very severely, and this means that if you look at the time integrated spectrum, all details of the radiation process will be washed out. So this means that we have to resolve individual pulses to be able to see exactly what the radiation process is. Another thing I want to point out here is that if the peak is related to the photospheric temperature, the F versus proportional to T4 gives a very strong reason for this correlation. Now, what does the spectrum look like? Now, most of the data that we have for time resolved pulses are still in the BATS catalog, but now Fermi is providing us with more of these data. I will first show you these data from the BATS catalog, which is 20 kV to MeV. And here we fit the data with a black body representing thermal emission and a Paolo representing the non-thermal emission. And the typical burst that we see, the spectra we see, is that the peak is represented by the thermal peak, but it's not dominating the spectrum. In other cases, which are more rare, it is the thermal component is very dominating. These are another examples here. The plots here on the left are band function fits for the same spectra as here, where the two-component model is fitted. And in this spectrum, you see that the residuals point that there is an additional component, which readily is captured by this non-thermal component. In this case here, another burst, you see the residuals with the band function fit shows that there is something down here, which is captured very well with the two-component. Very few bursts do have a pure thermal spectrum. This is a burst which is fitted with only a Planck function. It is a very good fit. And this is at a later time, and you see that the beam region is a point of flux about a few hundred kV. Now, as I showed you, the line of death where the synchrotron, these spectra are incompatible with the synchrotron emission. Now, if you plot the power law of this non-thermal component in this two-component model, you see that there are hardly none, not very many bursts which violate these synchrotron limits. Now, as I mentioned, it's important for us to have as broad energy. It's important to have as broad energy range as possible to see what the spectra are really doing. But there are only very few observations where you can divide up individual pulses in small energy time beams. Fermi is giving us a few of these, and these are just preliminary results of two of these cases. In this case, as you see in the lower part of the energy, the fit looks very much like typical BATS cases, weak thermal component, but there is only indication of it. And at high energies, there is a cutoff of the non-thermal component. The exact shape of it is not very clear. It could be an exponential cutoff. In this particular case, if you fit this with the band function, you can actually fit it too, but this case, it violates the line of death. Including this thermal component, the line of death is not violated. This burst is the here I've included the LAT data. It's a time-resolved spectrum of this famous burst 080960. See, the plots that Sinead showed you were time integrated over broader intervals, in pulses. If there is a thermal component here, it's very weak, and it will lie around 100 keV here. And the few cases we are looking at, it seems to be, and these are preliminary assumptions, conclusions, that the thermal peaks is quite, the dispersion of the thermal peak is not very big, but the break of the non-thermal component varies a lot. We have even seen a case where the non-thermal component reaches up to 100 MeV. This could be natural, since the thermal peak is only proportional to the temperature and the Lorentz factor, while if you assume that this is some sort of supertron component, it depends on the magnetic field and the particle distribution. Okay, so I've argued theoretically that one could expect strong thermal components, and I've showed you the spectra, and in many cases there is a strong thermal component, but in most cases there's only a weak component like this. The question is this conclusive? And we argue that the way of making this more conclusive is to look how the thermal component behaves. One could maybe imagine that this thermal component would behave completely erratic or something, but what we see is that a very distinctive recurring behavior of this thermal component, independent of if it's dominating or if it's a very weak component in the spectrum. And for the temperature, we find that it initially starts off at a high level and then it breaks off into a very good power. This occurs again and again, distinctive recurring behavior. Similarly, if we just look at the thermal flux, the flux of the thermal component, we see that it behaves like broken powder again. There's a rise and then there is a very good powder in the decay phase. The break occurs at the peak. These are for rigid pulses in that way. Now these are the distribution of the Paolo indices. It's quite a broad dispersion, but the sample average values are minus 0.6 here and minus 0.2 for the flux decay. Another thing we see, we can of course fit the normalization of the black body, and the interesting thing, we plot the ratio of the flux and the temperature and force power in the square root of this, because this is a dimensionless parameter which has a physical interpretation, which is the photospheric radius divided by the Lorentz factor. And what we see here, as a few examples, here is a pulse that rises and decays, and this is the normalization during the same period. And as you see, it grows as a power independent of how the pulse shape goes. And this is seen again and again. These are a bit more complicated light curves. Again, as you see, it's the normalization of the black body continues as a Paolo, much independent of the light behavior. These are a bit more complicated. This is just showing the recurring behavior of this Paolo increase of the pulses. And the distribution of this Pauli index is also rather broad. The average of the open sample is 4.5. So just to summarize what I've been arguing now is that from a theoretical point of view, there is arguments that say that it could be a strong photospheric component, but what we see is generally a non-thermal component. And we've been looking for if the thermal component could be hiding behind the non-thermal component. And by doing this over a narrow energy range with the black body and the non-thermal, they actually give a very good fit to the data. Fitting the broadband data, we can fit this with several components too, but of course the non-thermal component must be a bit more complicated. The important thing I'm showing you why this is something that is interesting is that if we look at the behavior of the thermal component, this is extraction of a part of the spectrum. It behaves in a very recurring and similar way from burst to burst, independent of its dominant or not. These results and understanding of what we are seeing from the photosphere, Asaf will talk more about this in detail. But since it's a photosphere, the physics is quite much simpler than from the internal shocks, so one can actually do quite a lot of extraction of data. We can calculate the photospheric radius and the initial radius of the outflow, for example. So I will leave that to Asaf. So around 100 kV, 100 kV.
What about those Paulo indexes? When you decompose your spectrum into Paulo and black bodies, you get the spectral index of the Paulo. Are they still consistent with the, or are they still inconsistent with Coulomb spectra, or are they more consistent now with Coulomb distribution?
They are more consistent with it. They are totally consistent with this was this is the distribution of this Paulo, and this is the Coulomb limit, and this is the synchrotron limit. So most of the slopes are consistent with even fast Coulomb, but there are a few which
but still there are some that are inconsistent.
Not consistent with
okay, so we still have the problem of fast Coulomb.
Problem for fast Coulomb.
As I remember, for example, if you take like photosphere radius like 10 to 13 and Lorentz factor like 100, then according to sigma T in 4, you will have too low temperature. How do you solve this problem?
Actually, what Asaf will show us tomorrow is that you can actually calculate the photosphere radius we get into the level.
You have very small photosphere and large Lorentz factor.
You show the fit of 080916C with a thermal component, and did you do a chi-squared fit of that? Because
yes.
In the analysis,
yes.
You know, the Fermi group, any departures from the band function were like 1 sigma at best.
Right. So the essential difference there is that that analysis we presented there was for time integrated. It was over a pulse. I mean, there's some. So any thermal component would be washed out. Otherwise, the fit there is not statistically superior from a pure band function, since the thermal component is so I mean, from a purely statistical point of view, you cannot argue for a thermal component. But what, for example, in this case here. If you follow the thermal component, it behaves very similar to this broken Paulo. Mm-hmm. So that is sort of an additional argument for this. But why I showed this was that if there should be a thermal component, the only way it can fit is around 100 kV. Mm-hmm.
How the relative normalization or the relative fluxes vary across the pulse of those two components? You probably have some of the figure.
So these are a few of the cases we've looked. Now this is the flux in the black body divided by the flux in non-thermal within this limited band. And so I mean, there's different from different bursts, and there's no recurring behavior. Sometimes it increases, sometimes it decreases. So there's no typical behavior. But in some cases it's you know, around 0.2, and in some cases it's quite high, over 0.5. But this is within the limited band, and in this case there should be a lot of emission up here in the component.
Okay, I have another question. Do you often need this Paulo component at low energies? Because if you could imagine that, for example, your photospheric emission is Comptonized further to high energies, maybe it's enough, then you don't have really a Paulo going all the way through your band, but it's just it's at high energies above the black body. Or sometimes you do have this Paulo.
Yeah, so, I mean, in principle, this is necessary to explain that the spectra are not too hard. I mean, otherwise they are not as hard as the black body typically. So I mean, it has to go through.
So basically, this tells that these are two separate components. This is not just one component.
It's not just black body components. Right. I mean, you could think about, I mean, for instance, if this is a pure black body, or if it's sort of some sort of distribution of black bodies downhill, then there's a simpler compound. But I mean, this is big question.
More complicated. Is there any more questions? Thanks for yours.